It's 3 in the morning, station time, when the alarm comes through. Not a klaxon, just a soft chime on Maria Chen's tablet, pulling her from shallow sleep. Bearing temperature excursion, agricultural drum 7. Deviation 0.8 degrees above nominal. Rate increasing. She's moving before she finishes reading. Drum 7 carries the potato and soybean rotation. It feeds several thousand people, assumption. The bearing is a ceramic hybrid with a rated service life of 15 years, assumption. It's been running for 11. And for 6 weeks, its temperature has been climbing in the pattern her team has learned to dread. The slow drift that means something inside is beginning to fail. The replacement exists, in warehouse 9, 8 kilometers away. Installing it means stopping the drum for 18 hours. The crops will experience uneven lighting, temperature swings, disrupted irrigation. None of that kills them immediately, but stressed plants ripple outward. Lower yields, higher nutrient runoff, more work for the algae bioreactors. Each deviation is small. Together, they compound. Maria reaches the control center. Her technicians are already running diagnostics. The bearing isn't failing yet, it's announcing that failure is coming. The question is whether that's 6 months away or 6 days. She makes the call. Schedule replacement for next week after the soybean harvest. A calculated risk. The kind that gets made here a dozen times a day. This is what it actually means to live in a rotating space habitat. Not the gleaming vision. Not the catastrophe. The in-between, endless management of systems that must work not just today, but for decades. The question is whether that's actually possible. Not in theory. In practice. An O'Neill cylinder is a rotating structure large enough to create artificial gravity through centrifugal force, supporting thousands or tens of thousands of people. Gerard O'Neill's original 1970s concept described paired cylinders 32 kilometers long and 8 kilometers in diameter, counter-rotating to cancel gyroscopic effects. The appeal is simple. Earth is finite, fragile, a single point of failure. The solar system contains more resources than humanity could use in millions of years. The logic, go where the resources are. But we're not suited for space. We evolved shielded by atmosphere and magnetic field, surrounded by a biosphere that recycles our waste without effort. An O'Neill cylinder attempts to recreate all of that artificially, at scale, and keep it running for a civilization. And the first number that changes everything isn't the cylinder's size, it's the shielding mass per square meter. Space is saturated with radiation, cosmic rays, solar particle events, high-energy ions that raise cancer rates and damage neural tissue. Earth's atmosphere provides about 10 tons of shielding mass per square meter overhead, plus magnetic deflection. A rotating habitat has no meaningful magnetic field. It relies on passive shielding, material stacked thick enough to stop radiation before it reaches living spaces. Engineers cite figures on the order of hundreds of kilograms per square meter estimate, depending on dose targets and materials. Lunar regolith, water, hydrogen-rich plastics. Each has trade-offs in mass efficiency versus acquisition difficulty. A cylinder 8 kilometers in diameter has enormous surface area. Even conservative estimates put total shielding mass in the billions of tons estimate. That mass comes from asteroids or the moon, not Earth, but it still must be mined, processed, transported, installed. Each step adds cost, complexity, time. The mitigations exist. Concentrate shielding around sleeping quarters rather than the entire hull, use water reserves as part of the shield, rotate crew schedules to limit time in less protected zones. But these add operational complexity and require tracking where everyone is, constantly. The shielding isn't optional. Without it, the habitat is a slow death sentence. In the medical wing, Dr. Samuel Mwangi pulls up the quarterly dose summary. Most numbers are within limits. 3 names are flagged. 2 maintenance technicians spent extra shifts in the outer corridors last month, where shielding is thinner. Their annual dose budget is 62% depleted with 4 months remaining, assumption. They need reassignment or reduced hours. The third case is harder. A structural engineer, 8 months pregnant, who worked in a partially shielded zone before the pregnancy was confirmed. Her cumulative dose is within margins. but the margin is narrower than anyone likes. Dr. Mwangi schedules 3 afternoon conversations. None will be easy. The technicians will push back. Their skills are needed outside. The engineer will ask questions he can only answer with probabilities. This is radiation accounting, ongoing negotiation between risk and necessity, tracked in spreadsheets, lived in bodies. Even if radiation is handled, the next bottleneck is quieter. Where does the heat go when there's no air outside? Every person generates heat. Every machine, every light, every biochemical process. On Earth, heat flows into the atmosphere, convects, conducts, radiates away. In vacuum, there's only radiation. And radiation is slow. A habitat holding tens of thousands might need to reject hundreds of megawatts continuously, estimate. That requires radiators, large panels glowing in infrared, dumping thermal energy into the void. Conservative estimates suggest areas measured in square kilometers. Assumption. These panels must be exposed to space, which means exposed to everything space contains. Micrometeoroids, debris, thermal cycling, UV degradation. The radiator problem isn't just area. It's what happens after the first puncture and the 1000th. Consider a representative incident. Assumption. Early morning, a sand grain-sized particle at hypervelocity punches through a radiator panel. The leak is small, a pinhole, but coolant pressure drops immediately. Within minutes, automated sensors detect the anomaly. Isolation valves close, sealing off the damaged segment, rerouting flow through parallel loops. Temperature rises slightly, then stabilizes. By next shift, a repair crew is outside. They locate the puncture with thermal cameras, apply a vacuum-rated patch, pressure test. Hours of work. But before the loop returns to service, the thermal team must rebalance loads, verify no secondary damage, update logs. The panel is offline for more than a day. This is routine. This is success. The crews call the smallest punctures dust tacks. Over years, punctures accumulate. Redundancy erodes. Crews spend more time patching systems that were supposed to be maintenance-free. This is where mission-critical small items appear. First, coolant hoses. Not glamorous, but a hose that cracks from thermal cycling or develops a slow leak takes down a radiator panel as surely as any impact. The habitat doesn't carry infinite spares. Second, isolation valves. When a line ruptures, survival depends on how fast that line seals off. A valve that sticks, closes slowly, or fails to seal completely turns a manageable puncture into cascading failure. A cylinder this large doesn't need one perfect seal. It needs a vast number of joints, valves, and interfaces that stay boring for decades. Airlocks, hatch seals, window mounts, conduit penetrations, expansion joints. Every one is a potential leak path requiring materials that resist degradation. Third, seals. O-rings and gaskets lining every hatch and viewport, made from polymers chosen for resilience across temperature extremes. But over years, they lose flexibility, develop compression set, absorb contaminants. A seal that tested perfectly in year 1 may fail quietly in year 15. Fourth, adhesives. They hold insulation in place, secure sensors, bond thermal protection materials. They have shelf lives. A tube that sat too long or was applied in wrong conditions creates latent failure that won't appear for years. The real stress test isn't launch day. It's year 12 when the habitat is running on spares you didn't predict. 5 years in, a pressure sensor model, used in water recycling, is discontinued by its manufacturer on Earth. The habitat carries a 5-year supply. That seemed generous. Now it's year 11. The stockpile is nearly gone. Procurement has spent 3 years qualifying a replacement with a slightly different interface. The work is almost done, but 3 more original sensors have failed, and 2 adapter brackets didn't fit due to manufacturing variations. In the water recycling control room, technician James Okoro runs the morning briefing. 17 original sensors left. Failure rate, about 4 per year. Assumption. Time to qualification, 6 months. There's a gap. The system will run with less redundancy, more manual sampling, more crew hours, more opportunity for error. No one will die from this. Probably, but it's one more layer of margin stripped away. And 100 similar stories run in parallel. Fifth, sensors. Tens of thousands monitor temperature, pressure, flow, vibration, radiation. When they fail or drift, the crew flies partially blind. Closed-loop life support doesn't fail with drama. It fails by drifting, one sensor, one microbial balance, one filter at a time. Air is recycled continuously. Water processed from humidity, waste, agricultural runoff. Food grown in rotating drums under artificial light. Each cycle depends on biological and mechanical systems in equilibrium. Sixth, filters. Particulate filters in atmospheric processing remove dust, pollen, spores. Their service lives depend on load, and load varies. A construction project kicks up dust. A crop disease releases spores. Filters load faster than expected. Seventh, pumps. Every circulation loop has pumps with bearings, seals, impellers. They wear. A pump running slightly below spec might not trigger alarms, but it reduces flow, increases pressure drop, forces other pumps to work harder. Eighth, bearings. We started with a bearing in drum 7. Bearings are everywhere. In pumps, fans, hatches, flywheels, centrifuges. They're load-bearing, friction-intensive, and often buried deep inside machinery. A well-designed habitat tracks every bearing, logs every temperature reading, predicts failures. But prediction isn't prevention. Someone still has to stop the machine, open it, replace the part, reassemble. That takes time and people. And during that time, the system isn't running. This is the maintenance backlog. Every habitat accumulates one. Every crew inherits deferred work and passes on more. The skill is prioritization, knowing what can wait, what can't, and what's quietly becoming an emergency. Orbital assembly looks feasible until you price the slow part: inspection, rework, and tolerance stacking. The habitat can't launch whole. Construction happens in space, piece by piece. Sections manufactured elsewhere, transported, joined in microgravity by humans and robots. Consider a structural joint. On Earth, you'd position sections precisely, clamp, measure, connect. In orbit, both sections drift, rotate, expand, and contract with thermal cycling. Alignment must be achieved actively, held by thrusters or manipulators, maintained through the joining operation. Then inspection. Is the weld complete? Cracks? Does the joint meet tolerance? If not, rework. Cutting, grinding, repositioning. Each cycle costs time, consumables, risk. Tolerance stacking means small variations accumulate. Plus or minus 1 millimeter across 100 sections can mean 100 millimeters of deviation, enough that final sections don't fit unless compensated. The mitigations are precision manufacturing, real-time metrology, adjustable interfaces. All add cost and time. The alternative is structures that don't hold air. Now the path forward. Not one leap, 3 phases. Phase 1, prototype. Perhaps 1 to 200 meters diameter. Assumption. Crew of 12 to 24, rotating through. Purpose, proof of concept. Success criterion, continuous crewed operation for roughly 2 years without evacuation. This prototype isn't self-sufficient. It relies on resupply, accepts elevated radiation exposure as known risk. But it validates rotation, reveals failure modes that only appear in real operation, builds institutional knowledge. Phase 2, mid-scale demonstrator. Perhaps 500 meters to 1 kilometer diameter. Assumption. Population of hundreds to a few thousand. Duration, years to a decade. Purpose, stress testing full integration. Success criterion. The population produces most of its own food and oxygen for several continuous years, with maintenance sustained by on-site fabrication. This is the valley of death, large enough for real complexity, not large enough for economies of scale. Expensive, difficult, unglamorous. But the skills developed here make Phase 3 possible. Phase 3, full-scale habitat. Multiple kilometers diameter. Tens of thousands of people. Designed for indefinite operation across generations. Success criterion. positive population growth sustained across a generation with no existential dependence on Earth. Even at full scale, problems don't disappear, they diffuse. The backlog still exists, just spread across more people. Life support still drifts, just monitored by more sophisticated systems. And then there's governance. In the main conference hall, the Habitat Council meets. 47 representatives from 12 residential districts, plus liaisons from engineering, agriculture, medical. Today's agenda: adjusting rotation rate. Current rate produces roughly 0.9 gravities at the rim. Assumption: a faction from lunar settlements petitions for reduction, energy savings, less wear on bearings, health impacts mitigated by exercise. Opposition argues the habitat was designed for near-Earth gravity, long-term health data favors it, children shouldn't grow up adapted to gravity they may never live in again. The debate is technical, political, cultural, generational. It can't be resolved by engineering alone. Someone must decide, and someone will be unhappy. This is the governance challenge. The habitat isn't a mission with an end date. It's where people live, raise children, grow old. Governance must survive disagreement without tearing the community apart. But there are limits. No vote can change thermal balance, override leak rate physics, or extend oxygen margins past what the bioreactors actually produce. No precedent exists for this. Every answer is an experiment. In the final third, we answer the only question that matters. If you could build it, would you still choose to live there? The case for yes. Earth is finite, fragile, one point of failure. The O'Neill cylinder is insurance. Not comfortable, not cheap, but insurance against extinction. The solar system contains resources to support populations orders of magnitude larger. The people who build these stations will develop knowledge and culture that can't exist elsewhere. The case for no, or not yet, the required technologies don't exist. ISS life support requires constant resupply. No one has tested whether humans can thrive in artificial gravity for a lifetime, raise healthy children in a rotating cylinder, maintain social cohesion across generations. The cost is measured in opportunity. Every engineer on this project isn't working on climate, poverty, pandemics. And there's risk of social failure, factionalism, governance collapse, a cautionary tale instead of a beacon. The middle path: build the prototype, learn what you don't know, accept it will probably be abandoned before its intended lifetime. That's research. Build the mid-scale demonstrator expecting redesign. That's iteration. Only then, if decades of operation prove the concept sound, begin full scale. This path is slow. Prototype before 2050, disputed. Mid-scale by 2070 or 2080, disputed. Full scale sometime next century. Most of us won't live to see it. That's the deepest lesson. Space settlement isn't a project for a generation. It's a project for a civilization, requiring investment in outcomes you won't witness. Institutions that outlive you, work your grandchildren will finish. And it requires humility. The concept might prove impractical, too expensive, less appealing than alternatives we can't yet imagine. In the quiet hours of night cycle, when greenhouse lights dim and machinery hums low, you can stand at the center of the drum and see the curvature of your world. Gardens rising on all sides. The structure rotating slowly around you. Beautiful. A world made by hands, but fragile in ways Earth is not. Every breath processed. Every drop recycled. The shell between you and void maintained by people who sleep, make mistakes, grow old. Wonder and wait, together. Maria Chen finishes her shift as morning lights come up. The bearing is stable for now. She walks home past synthetic grass and engineered trees. Someone had to be first. Someone has to keep the lights on. The rest belongs to those who come after.